Hi everyone, my name is Trevor Trinkino. I have recently started working with Andy Kershner of Kershner Trading Group to help him develop models and algorithms based on his trading experience, and we have been utilizing machine learning. So today I'm going to go through from a high level what machine learning is and how to kind of understand it in layman's terms. I'm also going to talk about the process that we've gone through to create this reversal strategy and some of the improvements that we've seen by utilizing machine learning. And then I'm going to talk a little bit about how any trader, whether they are fully discretionary or algorithmic, can begin to incorporate some of this stuff relatively easy to hopefully improve their trading. So from a high level, the easiest way I've been able to think about machine learning is that it is a function that has memory. And this function can go back through hundreds of thousands, if not millions of data points and find patterns within this data. And then it can find patterns of those patterns. And from these patterns, it creates a set of rules for itself. And it then stores those rules in its memory. So it can look at new data that it's never seen before, and it can make a prediction based on these rules. So I am specifically going to talk about decision trees and groups of decision trees called random forests. And we will get into exactly what those are in a little bit. So basically, from my experience with these machine learning algorithms, they're learning from the data. So you have to give them good data. Collecting data, collecting relevant data to the trade, and allowing the algorithm to find patterns within that data is what it's really all about. And that has definitely been the most important part of the entire process. Luckily, by using CloudQuant, we're able to collect a lot of data really easily. And because of this, we are then able to create better algorithms. The machine learning is able to make better predictions, and we're able to make some more money, hopefully. So first step that we went through is, we kind of defined what trade we're looking at. We wanted a reversal trade that had gone down, greater than 150% of the ATR since the open, and then the goal was to more or less catch the bottom. And what we did to collect data was, after the trade moved about 120% of the ATR, we started just placing entry orders at 10% intervals all the way down. So over in CloudQuant here, you can see here's our entry algorithm, and this is all the data that we're capturing at every entry point. So initially I think it was something like 140 different data points I was capturing at every single entry point on the way down this reversal. So that was, for some trades, it was 2 or 3 entries. For other trades, it was 20 entries. So we had a lot of data. And after we collected all of that data, CloudQuant makes it really easy to run a backtest and download this data and download these trades as a CSV file. So we collected all the data, downloaded the trades as a CSV file. I ran the backtest from 2011 to where we are right now in 2017, just to collect as much as I possibly could. These algorithms, machine learning algorithms in general, do better with more data, which is why I started with 140 data points and was collecting multiple times per trade. So from there, we're able to download a CSV file and then upload it into a Python notebook. This is a Jupyter notebook. For those of you who have never seen it before, it is easily downloadable for free. If you just Google download Jupyter notebook Python, makes things really easy to kind of visualize your data and work with sections of your code instead of running entire scripts. So this is the top of what that trades.csv file looks like. And we've got all of these different variables that we're collecting on the entry, anything from the average volume to the beta to down here. I know we've got a bunch of variables that I created that Andy and I talked about and we thought were going to be relevant to this reversal trade. Obviously, if you're collecting data that, if you're looking for a reversal and you're collecting data about the change in price from 2 weeks ago of a stock, it's probably not going to help too much. If anything, adding that data point might add some sort of noise to your data, and that could potentially actually hurt your algorithm. So what we did is we collected all this different data. A lot of it had to do with the money flow. A lot of it had to do with the geometric shape of the reversal, how it was, if it was accelerating downward, all sorts of things. And from there, this is the exact same file. I've just formatted it a little bit nicer, and I've boiled down those 140 data points to 30, just to make this a little bit easier to understand through this lecture. So here we go. This is our 30 data points that we've captured at every single entry. Once again, here's our entry algorithm back here, right here. Here are all the data points we're capturing. We are placing market entries at every 10% of the ATR down this reversal, just to purely capture the data, so that we can hopefully find the optimal entry point, and we can hopefully give the machine learning algorithm the data that it needs to find the optimal entry point. All right, so from there, this is just a little bit of Python code, pretty simple to get the names of all of our different data points. Another thing I should mention is that this doesn't take, this might be slightly confusing to wrap your head around right now, and I'll go into what specifically decision trees are and how they work in a second here, and hopefully that makes it a little bit easier to understand. But this doesn't take a rocket scientist to understand and figure out. Python is a fairly easy language to learn. I've been working on Python or working with Python for about 2.5 or 3 months, so not very long, and I've only been really diving into the machine learning world for the past 6 weeks. So very easy for anyone to pick up and hopefully start seeing some improvements pretty quickly. All right, so back down here, we have a list of all the different features or just variables that we have that are corresponding to each trade. Up here, we've got the top of our data frame. Each one of these rows corresponds to a trade, and all of these features is the data that's corresponding to that trade. And then at the end here, we have our entry price, we have our exit price as well. I think it might be hidden back in these dots right here. We've also got the highest price that the trade saw since we entered and the lowest price that it saw. So next step was to define what we're going to try and teach the machine learning algorithm. Initially, I was trying to teach it to find the maximum return at the end of the day, so the maximum end of the day return. We changed this to just the max return after we enter the trade because it's a reversal strategy, and a lot of times these things will pop back up and then kind of continue grinding down for the rest of the day. So, max return made the most sense for us today. This could be, the return to the next day for a different algorithm, or the return from today to, next week, or it could be the return in the next minute. It could be anything. It could even be the volume change. You can really make it whatever you want. So to get into what decision trees are a little bit more here, so you guys can kind of understand what I'm talking about. This is an example of one of the decision trees for the data that I collected from my trades.csv file. So what it does is it looks at all the different all the different data that you have, and it takes all the samples that you have. So I think I've got 145,000 samples, which is the same thing as saying 145,000 trades. And it looks through every single possible variable, all 30 of them, and then looks at every possible threshold of all of those variables to try and split these samples into two groups that are going to be the purest in the next nodes. And to explain what pure means, we can see here that there are 47,973 trades that we have labeled as a good trade, and 35,890 trades that we've labeled as bad trades. And we make this label back up here from this objective. So we've got our max return here. We assign a max return value to each trade. This is some really helpful, simple Python code that just kind of gives us some distribution statistics about what that max return is. So we can see here the average max return of each of these trades is 1.6%. The median is about 0.8%, so clearly we've got some outliers that are just skewing our data positively, which is good. You can see the 25th and the 75th percentile as well. So what we've done is we've got all of our data here, and we now just label each trade as either a good trade or a bad trade. So right up here I've defined what I want a good trade to be. So a good trade in this case is going to be any trade that had a max return greater than 1%. If we look back up here, that's going to be a little bit less than half of our samples are going to have a max return of greater than 1%. So now what we have is we have a data frame. This is just a simple Pandas data frame that has all of our features or variables in it for each trade, has our maximum return right here, and then it also has whether or not we consider that to be a good trade or a bad trade. So going back over here, this is our decision tree. We've got these labels, good trade, bad trade, based on how many of the trades in this little node are good trades or bad trades. So on the right we have 47,973 good trades, and the left we've got 35,000 bad trades. And once again, what this decision tree is doing is it's now looking through that entire Pandas data frame that we just created and looking through every single possible variable, every single possible threshold of those variables, and splitting our trades into two based on that threshold. So it does that, and then so up here we've got v2ATR to open. So this is basically a variable that's saying how much has the stock moved down since the open related to its ATR. When you're collecting data, you want the data to, you want to normalize it, and what that means is you want the data for a stock that's priced at $800 that moves an average of maybe $10 per day to correspond similarly to a stock that's priced at $10 that moves maybe 50 cents per day. And the way that I've done that in a lot of cases is I've just related everything to the ATR of the stock. So this is just what percentage of the ATR has the stock moved down since the open. If it is less than minus 0.073, then that's true, and we move down to this one. If it's not, then it's false, and all those samples go here. And then at this point, we do the same thing. So now is the relative volume at the minimum point less than 0.095? Well, if that's true, then all those samples go here. And if it's false, then all those trades go over here. And we just move our way down until at the very bottom here, we have all of the trades that made it down to this node. The majority of them are bad trades. Over here, the majority are good trades. So this is more or less how a decision tree is making its rule set. So when it's looking back at data, it can say, okay, is the V2 ATR to open less than 0.0773? Yes. Okay. Then we move that trade into this new one. And then it says, okay, is the minutes since open less than 0.7775? Nope. All right, then we move down here to this one. And then we say, okay, is the V2 ATR to minutes, which is another similar geometric variable that I created, similar to up here, is that less than 5.189? Yes, we move down to here. Now is the minimum relative volume less than 0.2955? No, then we go down here. And based on this rule set that it's created, that new trade that it just saw is going to be classified as a bad trade. So that's more or less how it's making a prediction. Is it looks back through all of the training data, all of the data that it hasn't seen before, and it makes these rule sets, and then it can apply any new trade to the same rule set, and the outcome will either be good trade or bad trade. All right, so back over here. So here's our Pandas data frame. We obviously don't want to, we have to test whether or not the machine learning algorithm is working or enhancing our trading in any way. And the way that we do this is we test it on new data that it's never seen before. So we create a rule set based on previous data. So right here I have I'm splitting my data based on January 1st of 2015. So anything before then, so January 1st, 2011 to December 31st, 2014 is going to be my training data, and then my testing data to see whether or not the machine learning algorithm is doing its job and doing a decent job of predicting is going to be from January 1st, 2015 to the present day, or the most recent day that I was able to capture data. So if we look down here, we've got about 145,000 potential trades that the algorithm can make a rule set for, and then we can test it on about 186,000. This step is not as important for decision trees and random forests, because as we saw, they're just making a threshold in a single variable at one time, and then creating a decision based on that, and then moving down to the next. But what I've done here is I have used this robust scaler, which more or less just centers and normalizes the values. For other machine learning algorithms, that is really important. The thing that we do need to do for every machine learning algorithm is we need to replace the Nan values. So if we go back up here, we can see that there are a couple of Nan values here for some of our data points. And that may have just been because there wasn't any data available for that trade at that exact instance, or the variable that we created for some reason didn't relate to that specific trade for the current day. There can be all sorts of different reasons why we get Nan values, and before you move on to this step, you probably want to take a look at your data and the data you've collected and try and minimize these Nan values as much as you possibly can. But at some point, you may just have some Nan values remaining, and you don't want to throw out that entire trade because it still has 28, or I guess this one, 27 good data points about it. There's just 3 data points here that are Nan. So we still want the algorithm to look at and learn from these 27 data points that are good and make rules based on these 27 data points. But we more or less want the algorithm to just kind of ignore this. And a machine learning algorithm can't do that just implicitly, because when that trade would move down to this node, it wouldn't know how to split it. So say that a trade had a Nan value for minutes to open. A Nan is neither greater than nor less than 0.7775. So where is that trade going to go? So that's why we need to clean up our data a little bit like this. Scikit-learn, which is just the package that we're using for all of this, SKLearn, makes things really, really easy. Another another reason why anyone can start utilizing this machine learning concept, even if you don't have any experience with it. But this imputer function takes all the Nan values and fills them with the median value for that variable. So if we look back up here at our data frame for these Nan values right now, the function is going to take the median of all of the min rvol values throughout the entire data set and just plop it right in there. And I've had questions on why did you use median versus mean or zero or interpolation, something like that. The reason I used median for, well, first of all, I tried all those. At the end of the day, you're probably not going to know what works best until you try it. So I did try all those. I think the reason that median worked best for my data set is because I do have a few outliers. So the mean was definitely skewed, and what you're trying to do with this is you're trying to get the random forest or the decision tree to just not pay attention to this value. You don't want the decision tree to create a separate decision based on some value that doesn't actually correspond to the trade. So say we gave a value of 2 to one of these trades that had a Nan value in here for min rvol. We gave a value of 2, and then back over here, this decision tree, when it's making thresholds, it now sees, oh wow, there's all these trades that have a value of 2 for the minutes open. We're going to create a new branch based on that, when really those values at 2 were just values that we gave it because it can't have Nan values. So you don't really want that. Median, because I have some outliers, was the best way for me to kind of get the machine learning algorithm to not pay attention to these Nan values. All right, so down here is our random forest classifier. What a random forest is it is just a group of individual decision trees that have just been created based on different subsets of the training data. So one example of this would be this decision tree could have been created based on only data from 2011 and 2012, even though our entire training data was 2011 through 2014. This one would just be created on a smaller subset of that, and there would be a set of rules that was made from this decision tree, and then there would be another decision tree that was created from maybe 2013 to 2014, and it would have a different set of rules, and then another one that was created from 2013 and 2012, and it would have a different set. And what it does is it creates all these different decision trees, and then it aggregates their rule set and aggregates their values to create its final rule set. And this in general will create a better prediction down the road. So this is the entire training function right here. You just do clf.fit, which is basically just random forest classifier, and you're fitting it to our X train and our Y train. Back up here, our X train is just any data that is before January 1st, 2015 that is corresponding to our features or our variables. And then our Y train is just a label that we gave it. So based on these features, is that a good trade or is it a bad trade? So the random forest classifier can now look through all this data, and it can make decision trees based on whether or not that was a good or a bad trade. These are all the different, called hyperparameters of the random forest. You don't have to worry about that right now. We'll get to that in a second. So this is what it's going to spit out. So we can do the clf.predict on our X test, and our X test is all the data from January 1st, 2015 onward. So it has never seen this before. And we've got our good trade or bad trade, the labels that we actually gave it. And then over here is the prediction. So you can see it's predicting a lot of zeros. It's getting some of them right down here. This is just for the first 20 trades. So we can go down here and actually look at different scores. So our accuracy score is how many times this classifier guessed the correct value. If we look down here, we have about a 66, 67% accuracy. So 67% of the time, this random forest classifier that we trained on our data before 2015 is guessing correctly for all the data after 2015. Another pretty major accuracy score or score for machine learning algorithms is called recall. And you can think of this in terms of baseball as out of how many strikes that are thrown, how many times does a batter hit a strike? So it's basically, we could wait until we saw a perfect setup, and the machine learning algorithm could, have an accuracy of, or a precision more or less, which is our next score. And precision basically talks about how many times it guesses. If it guesses a yes or guesses a good trade, how many times it's correct. And we could wait until we saw a perfect setup and only take those trades, and we would probably take very, very few trades, but we'd win almost all of them. But that wouldn't be super great because we'd be missing out on all sorts of opportunities and all sorts of good trades. So our recall score is saying out of how many good trades that the algorithm sees, how many does it predict correctly? And then precision is out of how many trades that it predicts to be a good trade, how many of those are actually good. So we can look down here. Our recall is about 60% of the time it's finding those good trades. 64% of the time that it guesses a trade is good, it is actually good. Down here we can look at what our maximum return was for the original data set. We have a mean of 1.5, a median of about 0.8, which we looked at back up there. This is with our classifier. We've improved this mean to about 24%. So we've improved it, or 2.4%. We've improved it almost 0.08% or 0.8%. Our median has improved from about 0.8% to a little over 15%. So the classifier is clearly doing a pretty great job at filtering out some of the bad trades for us. So moving down here, like I said earlier in the presentation, I initially had 140 different variables that I was assigning to each trade, and I've narrowed that down to 30 or so, and right here I've actually narrowed it down even more so to about 15 or 20. The reason that you do this is because, first of all, it takes a lot less time for the machine learning algorithm to run if it has less data to go through. Sometimes these algorithms can take a couple hours to run. Secondly, you don't want to be introducing excess noise. If you have a variable or a feature in your data set that just randomly has some sort of pattern in it that worked in the training set, and the decision tree makes a rule set and a bunch of rules based on this random pattern that it found, that's not going to generalize very well to your test set if that variable is not actually very important. So, similar to overfitting versus underfitting data, if you have too many variables, too many features, you have a higher chance of overfitting your data, and you have a lower chance of it working moving forward. So we can do this CLF.featureImportances. Once again, scikit-learn makes it really, really easy for us. And basically, it just tells us how important each one of our features were. And I create a filter so that I only want to include features that were greater than 3%, or had a feature importance greater than 3%. So I now have these features. I go down here, I do the exact same process that we did up there. I retrain a random forest classifier, except this time I'm using less features. We get that. And then onto these hyperparameters, they're called. They're more or less just ways, different ways or restrictions that the algorithm is going to learn. Scikit-learn gives you a really easy function called grid search CV, where you can more or less feed in a couple different values for these different parameters that you want to try, and it will run through and try all sorts of different combinations of them. So here we've got 3 possibilities for the n estimators field, we've got 3 possibilities for the max depth field, and 2 possibilities for the min samples per leaf field. So that's going to be about 18 different possible combinations that it is, or actually that's going to be about 54 different possible combinations that it's going to try. N estimators just corresponds to how many trees go into the random forest. So initially the default parameter is 10 trees, so it's going to make 10 decision trees, and then it's going to aggregate all those values together to make its final rule set. Here it's going to make 25, and here it's going to make 50 decision trees. Max depth, if we go back over here, just stops the decision tree at some point. I think this one, we've got 1, 2, 3, 4. So this has a max depth of 4. Initially, I think this decision tree had about 200 layers down, because it would just continue splitting the samples every single time to find the purest nodes. And by doing that, it was probably overfitting the data a little bit, because at the very, very bottom here, after it split the samples 200 times, it was only working with maybe 5 or 6 samples, and it was still splitting them based on tiny little patterns that it was finding, and it was creating these tiny little rules that were probably only corresponding to the previous trades and weren't going to generalize very well moving forward. So we kind of restrict how far down this tree can grow to restrict overfitting. And the same with minimum samples per leaf. We're basically just saying you have to at least have 4 samples to create a leaf node. Right here we've got 167, here we've got 90, so we're not really dealing with that right now. But if this were to continue, this would split to something around 45 and 45, and then that would split to something around 22 and 23, onwards and so forth. You would get it down to where you could potentially be overfitting the data. So right here we've got a max depth of 7, minimum samples per leaf is 1, which is actually just the default value, so it didn't do anything there, and then 50 decision trees. We run through the same process. We retrain our random forest classifier with less features based on the feature importances up here, and then also our optimized hyperparameters based on this grid search CV. And how this works is it will take our training set and it will break it out into smaller subsets, and it'll train a random forest classifier on that smaller subset and then test it on the data that it hadn't seen. And it just does this over and over again for different subsets with different combinations of these hyperparameters to then find which combination is the best. And this scoring function will tell it what score to optimize. If we go back up here, we could optimize accuracy, recall, or precision. I have chosen to use a scoring method called F1, which is just a weighted combination of your recall and your precision. So like I was talking about earlier, we don't just want precision because we're not going to be taking that many trades. We don't just want recall because then we might not be we might not be very accurate with every trade that we're taking. We might be taking a good amount of bad trades. So this F1 is a really nice combination of that. So from here, we retrain everything, and we can look at the improvements. So from using less features, boiling down our 30 features to 15 to 20, and using better hyperparameters, we've got a 2.5% improvement in our accuracy. We've got a 3.5% improvement in our recall, and a 2.7, 2.8% improvement in our precision. Down here, if we look at our max return statistics, initially we had a 1.5% maximum return mean and a median of 0.8%. That improved to 2.4% maximum return mean and a 1.5% median with the original classifier. After taking out some of the features and finding better hyperparameters. We've increased it from 2.4% down to 2.5%, and from 1.5% to about 1.7% on the median. And you can also see, because we use that F1 score and recall is part of that, that we're actually taking more trades. So not only are we making more per trade, but we're also finding more trades based on that grid search CV setting the scoring equal to F1. All right, so far we've just been talking about classifiers, and that's about all we're going to talk about today before I kind of run through the improvements that we've seen in our actual strategy. But I did want to just kind of introduce you guys to this example of a regressor, which is the same thing as a classifier, except it actually makes a continuous prediction. So you can just feed it in that maximum return value, and it'll try and predict what that maximum return value is. You can see here that it actually does a pretty decent job. That is great right there. But anyway, so back to our algorithm. This was the original equity curve that we had when we first came up with the strategy. We hadn't optimized anything. We hadn't spent any time on it. But this was the original strategy. Not very great. This was our strategy after we applied a classifier to the entry. So basically, that random forest classifier was giving us a thumbs up or a thumbs down to enter a position. Obviously, a pretty large improvement there. This next report is we were not only using a classifier to tell us which trade to enter, but then we were also using one of these regressors to predict what the bottom of the reversal was going to be, and we were placing our bids based on that prediction. So you can see here we're doing a lot better. And then finally, this is the most recent report. This is everything I've talked about up to this point, except we also used another one of these random forest regressors to predict what the maximum return was going to be. And then we placed offers based on that. So you can see here it's a pretty nice equity curve. If we go up here and look at some of the statistics, we have let's see. So we've got a compounded annual return on the average capital risk of about 32%. We've got a Sharpe on the average capital risk of about 3.2%. Our edge per share is about 2.7 cents. And we've got a daily Kelly win percentage of 4%, or 10%, and per trade 4%. So that is kind of just an overview of the process that we've gone through. I know it's quite a bit to take in right off the bat. I will continue to do some of these lectures where I dive a little bit deeper into each individual step, but hopefully that gave you guys kind of an overview of what we've done, and you feel like you could maybe start to implement it in your own ways. We've done it to find our entries and exits in an algorithm. If you didn't want to do that right off the bat, you could easily just have it as another variable or another feature in your algorithm. You could, discretionary traders could use it for anything from imbalances. They could try and predict if an imbalance was going to flip on them, and they could use a random forest to predict with a certain level of confidence whether or not that flip was going to happen. There's millions of different ways that you could potentially apply it. You could even apply it to your personal trade blotter. If you had data on every trade that you've ever taken, and the machine learning algorithm could then create a confidence level when it sees a new setup in the market, and it could basically tell you, based on your previous trades, this trade is probably one that you're going to make money on. There's infinite possibilities. But if anyone has any questions, please shoot me an email. It's ttrinkino@kershnertrading.com, TTRINKINO. I am happy to talk with people one-on-one or answer questions over email, whatever's easiest for people. All right, thank you guys. I appreciate it.